Welcome to CPE 350, Chapter 6.3. In this section, I'm going to introduce a function called the error function, which will enable us to apply the boundary conditions to our transient heat transfer problem in a semi-infinite slab and obtain a particular solution to the governing equation. So the solution that we had derived in the previous steps has two constants of integration and an integral that doesn't have an analytical solution. And what we have to do is just accept that there is a function out there, known as the error function, that has a form very similar to this term that's giving us trouble in our solution to the heat equation. This is the definition of the error function of y. It has a constant 2 over square root of pi, and then it's the integral between 0 and y of e to the negative y squared. So that's just the definition. And what we find is that this is a function that you look up the value for it in a table. You can't actually calculate an analytical solution for the error function because it's not an analytical function. And that's okay. It's kind of like the data that we measure. There's not necessarily a good fit to the data. It's just an x value and a y value paired up. So that's what the error function is. And now let's see how we can compare our real solution to the error function to arrive at a particular solution. So we'll start on the error function side and we'll multiply the constant, move that to one side. And then we're going to change out the y's for etas so it looks more similar to our solution. And then on the solution side, we're going to choose limits of integration between 0 and eta, and we're allowed to do this. And the reason is whatever limits of integration we choose, that constant of integration C1 will adjust accordingly so that the particular solution will always be the same. So in this case, we're actually choosing those limits of integration so that we can get a good match between our error function definition and our unanalytic integral. So these two highlighted functions are equivalent. And what I'm going to do is plug in the expression for the error function into our heat transfer solution. And so our solution then becomes a function of the error function, and I'm going to lump together all of the constants into another constant. We'll call that C1 double prime, just to simplify the algebraic expression. Okay, so at this point we have an error function solution to our equation, and we're going to still need to solve for the constants of integration. And we have our two boundary conditions. We started with 3 conditions, but the initial condition had collapsed with one of the boundary conditions. So we're down to 2. We'll put the first one in. We get that 0 equals the constants times the error function of infinity. What is the error function of infinity? You can look this up on a table, or you can enter it into Excel or any computational software. But the error function of infinity is just 1. So from our first boundary condition, we get that C1 is just the negative of C2. Okay, we apply our second boundary condition, and in this case, eta takes on the value of 0. And so the error function of 0, we have to go look that up. And conveniently, this happens to be 0. So then we get that C2 equals 1. And from here, we can plug in our values of C1 and C2 to get a particular solution to the dimensionless governing equation. And so this is our solution. And it has a very simple form. In fact, what we're also going to do is take one step further and redimensionalize it. So we're going to substitute back in all those parameters we substituted out. And this is just a matter of a bit of algebra. Processing through the steps. The point here is that we get an expression that is identical to the 1 if we were to choose theta equal to t over t naught. And so this just demonstrates, it confirms that the particular choice of non-dimensional parameters isn't always very important. And this is our full solution, and we can plot it to see how temperature is changing with respect to both time and position in this semi-infinite geometry. So at very short times, 1 second, the applied temperature, this temperature is T1, and this temperature down here is T naught. And so there's almost a discontinuity at early times, which gives the function this very sharp L shape. But after we relax the heat transfer for 1,000 seconds, the curve starts to round, as you might expect. We give it another 500,000 seconds, and it starts to smooth out, and eventually at longer times it becomes almost linear. If we were to reach infinite times, we would get a straight line at T1, but we're not going to go to infinite times. So this is just how the temperature is changing with position and time in the rod. And oftentimes when we have these kinds of line plots, we'll draw an arrow like this and say T to indicate which way time is increasing. I mean, obviously you can correlate the colors with your eye, but having that visual arrow is just a convention people include on their graphs.